So we're going to go through quite a bit today on how equipment is supposed to operate, and then how to make the measurements and how to determine how it's performing. So the other slides will be coming shortly after this. And Bill, if you would mute yourselves so you're not in the background, then we can go ahead and start the broadcast. I think everything's set. All right. All right. So first of all, I just want to recap this. This is really important because we're going to go over some things today that maybe we haven't that you haven't done before, and it all comes back to this. There are no theories in heating and air conditioning. This is all science. It's repeatable, universal, well-proven, understandable, and you can do it. And simply, we're making measurements to prove facts. And some of the measurements I'm going to talk about today aren't ones maybe you've traditionally done before. And I just want to make sure you understand that this all goes back to science. This is nothing new. You think about, we engineer these systems all the time to a 24,000 BTU system to do 24,000 BTUs of cooling. Somebody somewhere has measured that, and there's no reason we can't measure it in the field, and that's really what we're going to talk about today. I need to make sure you understand some basic things before we get into the meat of this, and I want to make sure you understand, first of all, that heat is a form of energy. And when we talk about heat, we oftentimes equate it with temperature, but temperature is really just a measure of the heat intensity. It's how hot is something. It doesn't quantify how much energy there is or how much work is being done. In other words, if I have a paper clip that's glowing red hot, it's 1,000 degrees Fahrenheit, and I take my fingers and put it on that paper clip, it's gonna burn, it's gonna hurt, but that paper clip will cool right off, right? And if I have an iron bar that's 3/4 of an inch in diameter red hot, and I grab it with my fingers will burn off before the bar gets cold. They're both the same temperature, but there's two different quantities of heat energy there. Paper clips, because it's smaller, can't hold near the amount of energy that the bar can, right? So that's why we have to get into BTUs. And BTUs are measurable heat quantity. It's actually an amount of heat energy. And what we're concerned with is two types of heat energy. We're concerned with sensible heat, which causes a change in temperature, which actually cools the air down, and latent heat, which is heat added or removed without a change in temperature due to change in state. That's when we're talking about removing moisture, removing humidity from the air. Total heat's a combination of both the sensible and the latent heat added or removed. When we talk about heat, it's measured in BTUs or BTUs per hour. It depends on whether they're talking about a mass or a mass flow rate, right? We're talking about 10 pounds of steel. We want to raise that steel up so many degrees Fahrenheit. It's going to take a fixed quantity of BTUs to do that. But if we had steel going down a conveyor belt and it was going down at 10 pounds per foot, well, then it would take so many BTUs per hour. We're talking about a flow rate at that point. But simply put, a BTU is simply the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. You've probably heard that over and over again. But what we need to make sure that we understand is what specific heat is, because specific heat is a quantity of heat required to raise 1 pound of a substance 1 degree Fahrenheit. If we're talking about water, and water is a substance, well, the specific heat of water is 1. But if we're talking about air, and air is a substance, a specific heat is 0.24. And the units of specific heat are simply BTUs per pound per degree Fahrenheit. So with air, it would take 0.24 BTUs to raise 1 pound of air 1 degree Fahrenheit. Different materials store energy with store a different amount of heat energy. You can see on this picture there, it takes about 30 times longer to heat water than it does gold, meaning that water stores a lot more heat energy than gold does. We talk about the quantity formula, right? This comes right out of chapter 1 of most good heating and air conditioning textbooks. Quantity Q is the number of BTUs equals a weight times the specific heat times the change in temperature. So, it's just simply, if we have X number of pounds times X number of BTUs times so many degrees Fahrenheit, that's going to give us a quantity in BTUs. If we have mass flow rate, then it would be Q dot, and that gives us BTUs per hour. So simply what we're talking about here is just mathematically, here's how it's derived. It's weight times specific heat times change in temperature. When we get into air conditioning, though, we have to take into account both heat and humidity. So the BTUs per hour equals the specific density, okay, which is a weight, times 60 minutes per hour, which is to get it to BTUs per hour, times the change in enthalpy. So basically what we're looking at is the specific density of air is 0.075 pounds per cubic foot. Now I'll show you that in a slide coming up here, times 60 minutes per hour, times our CFM, times our change in enthalpy. And enthalpy just takes into account total heat, both latent and sensible. So enthalpy is just a measure of total heat energy. Same formula, is just now revised for air conditioning. And really when it comes down to it, what we're talking about is when was the last time you quantified how much you conditioned the air, right? Because temperature drop won't tell you, your electrical measurements won't tell you, your gauge pressures won't tell you, and your superheat and subcooling won't tell you yet. That's what technicians measure to quantify performance. It's insanity because we're doing the same thing over and over again expecting a different result. And what I want to show you is there are better ways to make correct measurements the right way without hurting your frontal lobe, to get lab accurate results in the field, to get the job done right the first time in less time, and to guarantee the efficiency and capacity you've been selling. Simply put, if you're going to sell BTUs, we really should learn how to measure them. And if you think about this is the bizarre part of our industry. You know, we go out and we'll sell somebody a 2.5-ton air conditioner that does 30,000 BTUs of cooling. Yet we never really verify, you know, I'd say 99% of technicians never ever verify that it's actually doing the 30,000 BTUs of cooling that we sold them. And that's really what it comes down to. That's an assumption most of us make. You know, we assume when we buy a window air conditioner that's 12,000 BTUs that it's doing 12,000 BTUs of cooling. Well, if it's not installed properly and the side air intake vents are blocked off, it sure as heck's not going to work at its rated capacity. So these are things that we need to be measuring on a regular basis. And there's reasons we haven't measured them in the past, and primarily it was because we didn't have the instrumentation to do so. And the tools that we have weren't accurate enough. We didn't have ways of measuring humidity in a duct stream. We were using old wet bulb, dry bulb thermometers. We're using a lot of antiquated technology. Now, today, we can do things just as accurately in the field as we did them in the lab, a few years ago. It all comes down to one thing, and it comes down to making measurements. Any work that involves engineering, design verification, installation, service, or factory support, our goal when we're doing this is to design efficiency and capacity. It's performance the customer purchased. They bought a 13-plus SEER unit, and it also comes down to reliability. I mean, the customer at the end of the day, they want to make sure they're getting full capacity out of that unit at its maximum efficiency, and it's reliable. And if we do the performance testing and we make sure that at the end of the day the equipment's operating the way it's engineered to, all those things will fall into line. There's 10 steps to proper performance, and you need to make sure that you don't skip any of these things because we're talking about making the thing work correctly. All right. There are some things we have to do in the front end because this, again, is a field installed unit, so it's going to require a field installation and a field commissioning procedure. But what we want to make sure is done, we want to make sure we perform a load calculation so the equipment's the right size. And we need to know, obviously, if we're selling them a 2.5-ton system, that it's got 2.5 tons of load, right? We need to select a matching size of AC. Now, just because it's a nominal 2-ton doesn't mean it's going to do 2 tons of cooling. Depending on the coil configurations we select, the blower we select, the metering device we select, there's going to be some variability in the capacity of that piece of equipment. So when you're going through and selecting it, you're going to want to consider things like climate. In a humid climate, we may want to select a blower that has a dehumidification feature in it. We're going to want to look at the blower size because we may have a lot of sensible load to deal with out in Las Vegas, so we may actually want to run a higher, maybe closer to 450 CFM per ton versus 400 CFM a ton to get the maximum capacity out of the equipment. So, we really want to look at those things. We want to select a furnace and an air handler and a duct system that's designed together, right? Because you can't get furnace fixation where you're just looking at the appliance and that's all that you're focused on. You've got to remember that appliance is hooked to a duct system, and it's all got to be designed to work together. You want to make sure the outdoor unit's installed with adequate clearances to any obstacles. We don't want to put it underneath the deck where the hot air is going to recirculate through it. We want to make sure that we install it, the line set properly, brazing with dry nitrogen, right, to make sure we don't get oxides of nitrogen or oxides of copper in the tubing and cause contamination of the system. We want to evacuate the system using a micron gauge. We want to make sure we get below 500 microns because any moisture or air in that system is going to degrade the operation and it's going to significantly decrease the longevity of the equipment. We want to make sure we measure and adjust the airflow, adjust the charge using superheat and subcooling methods, and then obviously performance test the equipment. And this is the step we're going to focus on today. Capacity and efficiency are directly related. On a system, anything that you do to compromise the capacity of that system will degrade its efficiency. In other words, if you don't have the airflow correct, you have low airflow, you're going to get low capacity, you're going to get low efficiency. So, measuring the capacity guarantees that we're going to have the efficiency. In other words, if we can measure our capacity and make sure the unit's operating at full capacity, the only way it can get full capacity is if it's operating at its optimal efficiency, right? That's just, they go hand in hand. You can't have one without the other. And doing this testing, we can do a quick determination can be made where the problem lies. Do we have an equipment problem, a duct system problem, or both? Appliance and system performance. If the airflow is correct and the refrigerant charge is correct, we get those two things correct, then the system capacity should be correct. Those are the only two things we can adjust in the entire system. Okay? Yet there are two things that are often overlooked. We talked in the earlier seminars, 7 out of 10 systems have incorrect airflow and a little over 7 out of 10 systems have incorrect charge. Those are the only two things the technician can adjust, yet those are the two things that are most problematic in our industry. And when we check those two things and then this final test for checking capacity, it verifies those two things are correct and the system's operating at its optimal efficiency. Benchmarking the system simply assures that the customer is getting the design BTUs. And if you don't measure this, how would you ever know? All right. A couple things on commissioning, and I want to make sure you guys understand this, because too often technicians repair the appliance instead of the system. You got to remember, you got to look at this whole thing as a system when we're taking a system approach. Symptoms at the appliance often indicate problems elsewhere in the system. High static pressure at your furnace may indicate you have an undersized duct system or a restrictive filter. It doesn't mean you need a bigger blower motor. The blower's not working right. Okay, compressor flooding doesn't mean that we have a charge problem. It could be an airflow problem. We got to look at the system as a whole. It's imperative that we teach system commissioning and not just appliance startup. Okay, all these systems, because they're field installed, require a field commissioning procedure. Airflow and refrigerant charge are two of the most misunderstood and improperly adjusted parameters in our industry, period. And the question is, how are you addressing the problem? All right, so before we get into performance testing, all right, you've got to look at the obvious. Now, unless we're doing a test in, right, and some guys will do a test in, but want to see how it's performing as is before they do any work. But if we're going to test equipment, new equipment or existing equipment, the only way you're going to get maximum performance out of it is if it's clean, right? We're going to verify, after we get it clean, we're going to verify the appliance operation, and then we could also verify the system operation, in other words, BTU delivery to the space. Things like this, a plugged evaporator coil, obviously the system cannot operate at its optimal efficiency. Air bypassing a coil, we're going to have problems with efficiency. Or just simply dirty blower wheel. An 1/8 of an inch, or excuse me, a 1/16 of an inch of dirt on a blower wheel can degrade the efficiency, I believe, up to 60%. So, there's all kinds of things in this industry that we need to make sure we're looking at, and dirt's probably the biggest culprit we have out there. All right, so what are we going to need to do? Well, we're going to start with a visual inspection for duct inadequacies, dirt, things like that. We're going to verify our airflow. We're going to verify our static pressures within range, because believe it or not, when we talk about SEER rating, SEER also includes the amp draw of the indoor blower motor. Okay, so that's why you get a higher SEER rating with a PCM motor than you would with a PSC motor, because they take into account the amp draw of the blower motor. We're going to use digital gauges for better accuracy. Then we're going to measure return and supply wet bulb and dry bulb and calculate delivered capacity compared to the rated. and then if we have to, we'll recommend any corrective actions. Airflow always has to be set at the appliance first. So when we're benchmarking a system, we also want to make sure it's done first. Airflow is critical to system performance. Refrigerant charging requires proper airflow. Remember, you cannot get the charge correct until the airflow is correct. In fact, if you go out to a system, especially a fixed orifice system, and you adjust the airflow, you better check the charge. Because if you increase or decrease the airflow, you're going to change the way that system performs. And it could be undercharged or overcharged. A fixed orifice metering device, again from the last seminar we talked about, is charged to the airflow. We'll always set at a nominal 400 CFM per ton for air conditioning, and typically about 450 CFM per ton for a heat pump. Always refer to your manufacturer for specific instructions. After we set that airflow, after it's set, it's never adjusted to change system characteristics. In other words, what that means is if grandma's not getting enough air conditioning up in the bonus room over the garage, and the airflow has been set on the appliance, well, you don't run downstairs and jack up the blower speed to get her more air into the bedroom. That's not a airflow issue as far as the air handle or the furnace is concerned. It's a ducting issue. We need to increase the size of the ductwork or reroute the ductwork or find a restriction in the ductwork or whatever the problem is, but it's definitely a ducting issue at that point. We want to use a Vane anemometer to measure airflow. I've been doing this for probably capacity testing for over 10 years now, and I highly recommend the Vane. Can you use other measurements? Could you use a Pitot tube? Sure, absolutely. The reason I recommend the Vane is higher accuracy. They got very good repeatability. I've been teaching for going to my 12th year right now, and when you measure airflow with a Vane, when I have students measure airflow with a Vane, they can get very, very close to what I do time after time after time. And the reason is because they're not as subject to error as a Pitot tube or a hot wire are, and also they don't require density correction. So they make a very high repeatable, very repeatable measurement from user to user. A Vane, when you look at, there's two types of vanes we're going to discuss. One's a large vane, and that's going to give you a true velocity measurement. Again, no air density correction required. They're very, very simple to operate. They're required for proper commissioning of residential or even commercial system. But you've got to use something to measure the airflow. And if you have a single return like a flex ducted system with a central return, that's what you're going to want to measure the airflow with. If you have a ducted system, highly recommend the Testo 416 mini Vane anemometer. Very quick to get airflow, takes less than 3 minutes. You can do a full duct traverse with it, so you're going to get maximum accuracy. It uses a very low mass rotating vane, so it's a 1/2 inch diameter vane, and it's going to respond very well to changes in there. And it's got jewel bearings, so it's very durable. And again, the reason we spec a vane is there's no air density correction required. All vanes, when you get into smaller vanes, it's non-invasive measurement, and again, forgiving the operator error. If you want to use a Pitot tube, and here's a picture of me doing a Pitot tube, and you can see here a couple things I just want to make note of. Number one is I use dry erase markers. Oops, let me go back here. Sorry about that. Let me get up a marker here. Felt tip pen. All right. If you look on the ductwork right here, you'll see some of my scribble. I use dry erase marker a lot when I'm working on a job, and I can just write on the ductwork and then erase it off when I'm all done. And one of the real key things if you're going to use a Pitot tube, you have to make sure you do, because the Pitot tube is like the least expensive way to get into measuring airflow. You know, a Pitot tube and a manometer, a high accuracy manometer like a Testo 510, or even a blower door gauge. If you have a blower door gauge already, that'll work fine. But what you have to do is you have to measure each velocity pressure and then average the velocity, or excuse me, get your average velocity pressure in the system. Then after you get well, back up, I'm sorry about that. If you use the Dwyer calculator here, which I'm showing on the side, this is just a little app where you can put in your velocity pressure and your air temperature and your barometric pressure and your relative humidity, and it'll actually calculate your, if you scroll down a little further than I can on that screen there, it'll actually calculate your velocity. And what you'd have to do if you're going to use this is you're going to have to do it for every single point you measure airflow. So every single one of those points you've got to put in the air velocity. And after you put in the, so you're going to use this app if you make 16 readings 16 times. You put in 0.23, 0.24, 0.27, 0.68, whatever you read in there you're going to put in, and it's going to calculate a velocity. You'll record all those velocities down, add them up, and then average them, and then you get your average air velocity, and you have to multiply it to get your CFM. Pitot Tube, I have some directions on our website on how to use one. It's the least expensive method. It's the most labor-intensive method. So it's one way or the other you're gonna end up paying for it, whether it's a little bit of time or it's a or we end up with time, or we end up with you're paying for it by time or you're paying for it by price. Your choice. Wet bulb. We typically recommend the 605H2 for accurate wet bulb measurement. Wet bulb has to be measured within 1/10 of a degree resolution. The 605H2 has a very high accuracy, reliable sensor for the cost. It's a very inexpensive way to get a high accuracy humidity reading compared to other instruments. So, there are other instruments out there that you could use for this, but this is the one we recommend. We actually have been doing this for quite a while. We have quite a few programs running successfully, and so some of the tools we're recommending are simply because we know they work for this application. Just to give you an idea of why the accuracy is so critical, 1/10 of a degree of wet bulb difference results in 1/10 of a ton of cooling difference. So if your wet bulb measurement's off, if you're not getting an accurate change in wet bulb, you're not going to get an accurate reflection of what your capacity is doing. Problems inherent with your instrumentation will lead to misdiagnosis. We're measuring capacity so we can determine if the system's operating properly. You don't want to be chasing your tail because you made bad measurements. And that's often where we see the problem at. Either somebody doesn't know how to use the tools that they use, or they're using tools that aren't accurate enough for what they're trying to do. You got to remember, all tools aren't the same accuracy, and they don't all need to be the same accuracy. If we're just trying to determine between 4 blower speeds which is the correct blower speed to select off a PSC motor, well, we don't need a highly accurate airflow measurement to determine that. We can do that with static pressure measurement and say, okay, at 0.3 static, I'm moving at 1700 CFM, I'm in the ballpark. If I need 1600, I'm in the ballpark. Fine, that's all you need to do. But for what we're doing now, if we're talking about measuring capacity, we need a very, very accurate measurement of our enthalpy, and we're going to derive that from wet bulb, and we need a very accurate measurement also of our humidity. Excuse me, of our airflow and humidity. So that's 2 things you can't skimp on there. One thing you should realize is technician after technician should always get the same measured results. In other words, if I go out and measure your capacity on the job, you should be able to come right up behind me and make the same measurements and get the same answers that I do within reason. Typically within 2 or 3%. And you need accurate instrumentations to do that. If we're going to get the charge correct, we recommend a 500 series analyzer simply because they're higher accuracy, greater speed, real-time calculations, all in one tool. And we can also work in the low ambience. And if you get into Testo, you get into the graphic capabilities, which is nice. The system charge, again, we're talking about performance. The charge is critical. We've got to have correct charge in the system. We want to charge by superheat and subcooling because that's the most accurate method to get that charge correct. Superheat verifies on a fixed orifice that the evaporator is performing properly, and subcooling assures there's adequate refrigerant for per metering device operation with the TXV. Here's the key thing, is any charge but the correct charge will negatively affect system performance. Now, I didn't go over the first several slides in here as an infomercial to try and sell you tools, even though, and I hope you buy them from us. I hope you buy the tools to do the job right. What I'm trying to explain to you is that the testing I'm going to show you, you can't do with a standard sling psychrometer that we're going to, that you'd have a wet bulb or dry bulb sock. You're not going to slide a cotton swab over a Type K thermocouple and be able to do this type of testing with any kind of accuracy. we've got to make sure if we're going to start benchmarking a system, and we're going to have the anticipation of coming up with the BTUs that the manufacturer engineered it for, you're going to have to use accurate tools to do it. That's the only way. You got to have the airflow correct, you've got to have the charge correct, and then you've got to make accurate humidity measurements and wet bulb measurements across that coil. If you don't do those things, you're not going to get the rated performance out of the system, and you're going to be really frustrated with this. So that's why we focused a little bit on the tools there, is to make sure you understand what the expectations are. We already know that 7 out of 10 systems are not set up correctly, right? Charge and airflow issues. People are typically using manual gauges, analog gauges, and if they're making a wet bulb measurement, they're typically not using instrumentation that's accurate enough to get the charge correct. And if they're using charging charts, which most of them don't, their instrumentation's not accurate enough to get the correct readings to even use those charts properly. So you've got to make sure you're using the right tools for the job. All right, calculating cooling capacity. This is easy. It's as easy as 1, 2, 3. I've been teaching this for 12 years in my classes, and I have high school kids doing it all the time. The kid doing it here, he's not even a really smart kid, okay? And believe me, if this kid, Andy, could do this, any of you guys could do this stuff. All right, so we're going to talk about the method here. Andy's using a Vane anemometer to measure airflow. You can see his technique is very good there. The vane is nice and perpendicular to the airflow. He's measuring in a nice tall return air drop, and he's getting airflow on the system. He's measuring 3 points in the duct system because we're doing a traverse of the duct. Those holes, the outer 2 holes, should actually be drilled at about 1 inch off the surface of the wall, then a center hole to get an accurate reading. This is an older picture before I really knew what I was doing with airflow, and since then, we move in about 1 inch off the ductwork typically and measure from the side, the narrow side of the duct, because the probe's about 36 inches long. So you only have to make 3 holes in the duct then typically. Unless you're doing like a 12 or 14-inch wide drop, then you might have to drill a 4th one in there. Typically, we'll use a plastic plug to plug those holes when we're done. That way, you might tell me, oh, the customer doesn't want me to drill a hole in the ductwork. Well, you go to any commercial job, you go anywhere to measure airflow, you have to make a hole in the ductwork to measure airflow. There's no way around it. You've got to somehow do that. Even if you're going to measure temperature, you're going to make a hole in the duct. The key is just putting a nice plug in there so it looks good when we're finished. All right, so let's talk about the manual calculation performance. Step 1 is to measure. We're going to get airflow in the return. We could be using a large vane. We could be using a small vane, but we've got to get an accurate airflow measurement. If you're going to use a Pitot Tube or a hot wire, because maybe you already own one of those instruments, you need to make sure that you take into account air density and correcting the air density. In other words, getting the pounds mass flow rate across the coil correct. Because not only is there air density playing impact on performance of the equipment, it also affects our airflow measurement. So we've got to make sure that we're taking that into account. We're going to measure also entering and leaving wet bulb around the coil, around the heat exchanger. So we're going to measure the wet bulb and dry bulb in the supply and the wet bulb and dry bulb in the return. We're going to use a chart to then find the change in enthalpy. So you can see here, and I'm going to show you a chart, the next one here. We can use an enthalpy lookup chart or a psychometric chart. In this case, it used a program here. We had point of 78 and 58, and our enthalpy was 25.01. Right? H is the symbol for enthalpy. If you want to download a free chart, if you just go on TruTechTools.com and you go to type enthalpy in the search box up there, you'll find a copy of this enthalpy chart. And I want to make sure that you understand how to use this chart because it's a little tricky at first if you don't understand it. So let's say that we had a wet bulb temperature of 51, I don't know if I can draw with this thing, we're going to try it or not, 51.3, okay? If we had a wet bulb of 51.3, the way you'd read this is this is the whole number, the 51, then you have to go to the 0.3 column right here. So the enthalpy is 21.03, right? It's 51, and then the tenths of a degree up here at the top, right? 51.3. So 51.4, you go to the next column. This is why you have to have a wet bulb thermometer that reads accurately to the tenth of the degree. The Testo 605H2s, if you set 2 of them side by side, and you really have to put them almost in a plastic bag or a baggie to let them stabilize for a second. You'll see they're usually within 1/10 of a degree of each other. Again, 1/10 of a degree, a wet bulb equates to about 1/10 of a degree, 1/10 of a ton of cooling. So we don't want to have, ones that are a degree or 2 degrees apart of the wet bulb, because it's going to drastically throw off our readings. The other one thing you can do is you can use a single wet bulb thermometer to make the measurement. However, you have to wait for the wet bulb thermometer to stabilize. And if you have if the load's changing quickly, you may run into some problems with that. So we do have guys that use a single wet bulb thermometer, and you can do that, but it's oftentimes not the easiest way, and it's not as productive as having 2 wet bulb thermometers where you can just throw one in supply, one in return, and determine the change in enthalpy. So, if we had to calculate our first enthalpy, it was 51.3. We'd get it here. Then maybe our second one, was, let's say 40.6, right? Then we hit that there, and we just subtract these 2 numbers from each other, and that's our change in enthalpy. And that's all there is to using that chart. Oops, wrong one here. Go back to the arrow. All right. All right. Step 3 is simply to calculate the capacity. So all we're going to do is we're going to put in this formula, and this is a standard air formula, and I'm going to explain to you a couple things here when we get a little further on here. The standard air formula is simply 4.5 times the measured CFM that you have times the change in enthalpy, and that's going to give you tons or BTUs per hour. Okay. Or with program, and if we use a program like the psychometric program, it's going to automatically do some calculations for density correction. Here's how that formula works, and it's pretty simple. So I just want to show you how the units cancel out, but this is BTUs per hour. This is 0.075 pounds per cubic foot. This is the density of air, okay? Pounds per cubic foot. So there's 1 cubic foot of air. A cubic foot of air weighs 0.075 pounds per cubic foot. So that's the density. 60 minutes per hour is cancels out the BTUs per hour, because we have airflow in CFM. This is 400 feet cubed per minute. And then our enthalpy change would be 6.66 BTUs per pound. Now, but look at how these units cancel out. Pounds here is going to cancel with pounds here. Feet cubed will cancel out with feet cubed. Minutes will cancel with minutes. And that leaves us with BTUs per hour. Okay, so if we multiply these 3 together, 0.075, multiply across the top, right, times 60 times 400 equals 6 times 6.66 is 12,000 BTUs per hour. That's all there is to it. This would be at one ton of cooling. Now, this number here, this 6.66, this is always, if we have a nominal 400 CFM per ton, that number will always be 6.66. That's a typical change in enthalpy. It's engineered in every single coil, okay, to make it operate correctly. So when you're looking at your enthalpy numbers, if your target enthalpy is 6.66 or close to 6, you're like 6.1, 6.2, 6.7. You're right in the ballpark where it should be. Your airflow is going to be a little higher, a little bit lower than nominal. If your enthalpy is much higher than that or much lower than that, you've got airflow issues you got to take a close look at. Capacity calculation, the 4.5, I showed you where it's derived from. This is what we typically use for field calculation. Some programs correct for air density, but if I'm in the field and I'm just doing this, mathematically with my calculator on my phone, I'm probably going to use 4.5 times CFM times change in enthalpy. That's going to get me well within the ballpark. It's going to be well within 2 to 3% of the measurement. If you get outside of standard air, okay, let's say that we're at this point right here, and this point here is 80 degrees Fahrenheit at 80% relative humidity. Well, that's going to change things for us, right? We might run across this like Ohio right now. It's summertime here. You're going to do a startup on a new piece of equipment, and all of a sudden, it's hot and humid in the house, and you're getting the equipment commissioned. Well, how does that affect the operation of the equipment, right? Well, if we look at these lines, let me see where my mouse went. Here it is. These lines right here, you'll see this is 14.5 specific volume. This is the specific volume of the air. So here we're at 14.5, here we're at 15. That puts that specific volume at 14.79 feet cubed per pound. If we take the reciprocal of that, okay, that's 0.068 pounds per cubic foot. Now, we talked about earlier that standard air, standard air was 0.075. So let me show you what this changed for us. So we're at Ohio at 1,500 feet at 80 degrees and 80% relative humidity. We're actually going to need more airflow than our nominal airflow. And if you were at the earlier webinars, we talked about a little bit about mass flow rate, but 30 pounds per minute divided by 0.067, our nominal CFM now would actually turn to about 448 CFM per ton. So what I'm telling you is on a hot, humid day, we're probably going to need a little more airflow when you set up that equipment initially than you would if we were making our measurements in with standard air. And I'll just show you how this would work here real quick, because now instead of this 0.074, we're at 0.067, right? 0.067 pounds per foot cubed times 60 times 448 times 6.66. You can see here that because we have a lower mass, a lower density of air, right? Fewer pounds per cubic foot, we have to move more of it to keep the mass flow rate across the coil the same. All right. So this is typical stuff we might run across. Why density matters? Because if the density is low, you got to have more CFM required to keep the mass flow rate the same. And if you don't consider air density when we're setting up a system, you're going to have very low airflow. All right, so let's talk a little bit about how to make the measurements. There's a couple things we can do. Real-time performance. We can actually, there's tools today that calculate real-time heating and cooling capacity that use the ASHRAE calculations, current psychrometric calculations. They'll do all the compensation for air density and humidity, pressure and elevation, temperature. They can average, print, logs, downstream data, but you're going to pay money for them. They're a little over $2 grand. The real-time, it's actually, and this is a test I did on a furnace, actually my own furnace in my house. The real-time readings, it's going to use a mini Vane, or they make a large Vane anemometer that goes into a Testo 435, and 2 wireless probes. One probe goes into supply, one probe goes into return, and literally in real time as you make your airflow measurement, it's printing out the BTUs as we go. So you can see that furnace was doing 81,881 BTUs per hour. It was 100,000, 80% efficient furnace. So I'm measuring airflow and BTUs at the same time. It'll work for heating, it'll work for cooling, it'll work for heat pumps, electric heat, whatever you're using, you'll measure BTUs per hour. I have a contractor in Tennessee, Eddie Leverage, who uses this tool, and he absolutely loves it because he goes in, every job he goes in, he tests in, he shows his customer how their equipment's currently operating. It's a great lead into either system repair or system replacement. A lot of times just showing a customer that their system is old, it's dirty, it's operating way below its rated capacity is all that they need to see in order to justify replacement of that equipment. So these types of things, especially when we're commissioning new equipment, to be able to document that when you install the new equipment, it was operating at its full capacity, go back in a year later and go ahead and check that equipment again and show the consumer now that it was operating at 81,000, but now that the filter's dirty and the blower's a little dirty, it's operating below its rated output, right? So now we need to go ahead and clean it and then test out again. It's a very quick, easy way. It takes less than a couple minutes to actually have that reading in your hand. If you hate math and you want to do it by hand with a wet bulb thermometers, there's an app for that. I can't remember whether it was free or it was just very low cost, a couple dollars. But I actually have this on my iPhone. I use it quite a bit, and it's really slick because it does your air density corrections for you. So you can enter your altitude in feet, the current altitude you're at, and that's going to correct for barometric pressure changes. And then you're going to put in your entering dry bulb and wet bulb, you're leaving wet bulb and dry bulb, then your airflow, and you want to use ACFM, which is actual CFM if you're going to use a Vane anemometer. And it'll calculate for you. You can see here with that information I put in there is 27,853 BTUs of cooling. And that's actually closer to 2.5 tons. This doesn't round in the half. It's 1 ton increments. Shows you your sensible, shows you your latent, and it shows you your moisture removal in pounds per hour. So this is an iPhone app. I mean, it's pretty slick, pretty simple. It allows you to make the same measurements, very inexpensive. I shot a screenshot of this, and I emailed it to myself. So on an iPhone, if you hold the top button and push the center button on the iPhone, hold the power button and then push the center button, it takes a screenshot, and I emailed the screenshot to myself. You could easily do this with your customer, shoot them a screenshot of when you came in, shoot them a screenshot when you left, and show them exactly what happened. And this nice thing is, too, you have the time you came in, recorded it, and you also have the time when you left. So a pretty slick, pretty simple way to do things. In order to do this, we gotta have, again, lab accurate tools, and field instruments are available with lab accuracy, and we covered that already. Now, measurements on their own, right? Because you're going to make these measurements, and unless you know what the output should be, they mean nothing without a knowledge of the equipment design, right? And just like your doctor, he needs to know what your body temperature should be before he measured it, right? You want to get your temperature taken, and he goes, oh, it's 103 degrees. That's interesting. All right, well, come back in a couple more weeks, and we'll see what things are going on. If you missed that, you had elevated body temperature, you had an infection, you died, you can sure as heck bet some lawyer somewhere is going to figure it out for him, okay? We need to make sure we understand how the equipment is supposed to operate. And typically it's designed under ARI design conditions, and that's the way it's engineered to run. When you talk about operating conditions and installation, both have an impact on capacity. This is a extended chart I pulled off of a manufacturer's, Comfort Maker's website. I just went on there this morning, and they have these in their installation directions. Train, Carrier, Lennox, everybody has these. They may be a little bit different format, but these are the things we've got to look at. And here's what I want to show you. So this extended refrigerant line length, right? You can see this system is engineered to operate correctly with a 25-foot line set. If we got up to a 75-foot line set, well, it's going to drop 2% of its capacity. It's going to operate at 98% of its capacity. If the system were installed on a light commercial job and it had 208 voltage, it's going to lose another 0.98, or another 2% of its capacity, right? If the airflow was at 95% of its rated airflow, well, 0.99, that's a 1% drop. And then if we're testing this piece of equipment and it's 95 degrees outside, but we're at a 63-degree indoor wet bulb temperature, right, and 75-degree dry bulb, again, we're going to be at 0.95, okay? When you multiply those together here, 0.98 times 0.98 times 0.99 times 0.95, we actually get 0.90, which is very typical for field conditions. Right now you may have a 25-foot line set and it's multiplied times 1. Now it doesn't come into effect. You may have 240 voltage. Now the voltage doesn't come into effect. You may just be multiplying to 0.99 because we have low airflow times these conditions here. But what you got to see here is it's very, very typical. If we took 24,000 BTUs to end up with 21,678 BTUs of output, and reality sometimes bites, right? Because you're hoping you're going to get the full 24,000 BTUs of cooling, but there are associated losses. If you have low airflow, you've got low capacity. If you've got low voltage, you're going to have lower capacity. If you've got a long line set, there's energy that's being absorbed by that line set that you have to reject the condenser. You're going to have a decrease in capacity. So installation, we have to make sure that we take these things into account when we look at the equipment. And here's an interesting one here, is equipment we talked about earlier in the presentation is designed, engineered for these conditions. 67-degree wet bulb at 80-degree indoor dry bulb conditions. 67 is 50% relative humidity. At those conditions, you'll get 100% of your rated total capacity and 100% of your rated sensible capacity, okay? We talk about sensible and latent capacity. What we're talking about is our sensible latent split. It's the ratio of heat to humidity the appliance is going to remove. As we increase and decrease airflow, the latent sensible split will shift, and we'll get either more or less humidity removal. If we're higher, like you can see over here, where this 110's at on the indoor airflow correction table, if we're at 110% of our rated airflow, well, we'd actually get an additional 3% of capacity. So, like I said, if we were in Nevada and humidity wasn't an issue, we might want to be at 450 CFM per ton. We might want to be at that extra 10% of airflow to get that additional sensible capacity out of the machine, because we simply don't need to remove humidity. But if we're here in Ohio where the humidity gets high, we want to make sure that we have that airflow correct. Typically we don't want to drop below 400 CFM per ton, because once we do that, we start to, even though we get a little bit more humidity removal, we start to lose total capacity of the system. So unless you're engineering it for that, and humidity is your primary concern, and you're engineering it for lower airflow, once the airflow drops, the capacity drops. So very important thing to realize. All right, I want to talk a little bit just about what you're gonna see, because I think you'll be shocked when you get out there. This is an example of a pre and post test of a system. Pre-tested a 5-ton carrier system, and 44% of its rated capacity was operating at. Post-test, it had 100% rated capacity. So what happened? What did it look like? Well, for starters, this 5-ton system had extremely low airflow. It's running 0.54 static in return and 0.52 in supply. So it's running over an inch of total external static pressure. The system is rated at ½ an inch external static pressure. That's a huge, huge problem. The biggest thing it came to is a blower could not overcome a poor duct design. So we had a delivered capacity of about 26,521 BTUs. So we got a 5-ton system that's putting out about half of what it's supposed to. Now, the interesting thing is you go out to the system, and the suction line's cold, the liquid line's warm, there's cold air coming out of the registers. But again, if we don't measure the quantity of cold air, we don't measure the BTUs coming out, how do we know how much is there, right? And this is where it's so important. We had 42 degrees of superheat. The target was 20, so we had high superheat. We had a delta T across the evaporator of 4.9 degrees and a delta H, a change in enthalpy of 5.3. So how many techs, the question I always have is how many techs have this information before making a decision on the course of action, right? If you're not measuring BTUs, you simply don't know what the system's doing. With practice, this takes about 20 minutes to get all this information, okay? What's interesting is, if you really think about it, the only thing extra we're doing is measuring supply air, wet bulb, and dry bulb. We have to measure return air, wet bulb, and dry bulb to charge. We have to measure airflow to make sure the system's right. Once the airflow is measured, it doesn't change. So that's a given. And so we measured the airflow. We throw 2 wet bulb thermometers in, and we're not making taking any more time than we should to properly commission a system. When we looked at the post, we got the airflow up to 2014 CFM, 100% of its rated design. Return static was 0.53, supply 0.47. Still high on there on the supply and return air static. Now what happened was, and we made some corrections on here, we couldn't get the static down much further than it was, because what we're exceeding was the pressure capabilities of the blower. Even though the statics didn't change much on this, the flow changed quite a bit, and I'll show you why at the end. But we had delivered capacity of 59,997. We got the charge correct, and you can see the enthalpy was 6.62, which is right on the money for where it should be. So how did it get there? Well, the improvements performed was, number one, this thing had a dirty blower wheel. And the big thing that would change here was that all the flex duct was changed from 6 to 7 inch. So at the same static with a larger duct, we simply got more flow through there, okay? We actually tried to get the ductwork larger, but there was just some physical limitations. That 7 inch was as big as it was going to get and get the system installed. Is this the way I'd like to see it? Absolutely not, because I got an evaporator that's on a highest speed that it can be. It's working as hard as it can, and it's eating up some sear on the equipment simply because the duct system's not designed properly. However, this is a huge, huge improvement. We're getting now twice the amount of cooling out of that system. And is it perfect? No. Is it working much, much better than it did before? Absolutely. And obviously we had to add some refrigerant to it to get the charge correct. Typical results, if you start measuring capacity, you will typically see around a 27% increase in cooling capacity. And this is done off of, I think, around 7,500 tests by Clear Results in Arkansas. There's hundreds of dollars savings per system, often less than a 1-year payback per system. And doing these few things is going to really reduce your trouble calls and your maintenance. You're going to get, it's going to operate much, much better. Less guessing and more getting it right the first time. The entire AC tune-up, again, includes the entire system. We're going to focus on airflow, charge, and delivering commissioned air, and ultimately quantifying the performance. Some results that you'll see, an average of about 0.27 kilowatts per ton in peak demand, and a 99% confidence in these from a 7,500 tune-up sample. An average of 500 to 1,500 kilowatt savings annually on heat pumps and air conditioning. So there's a substantial amount of electrical savings by getting the equipment running properly. How do we turn this into a new profit center in our business? Simply, it doesn't happen by yourself. You need to educate your customers. First of all, you go out and start making these measurements, your customers will come to expect those things. And it's really quite interesting because it opens up a lot of room for conversation, and also it's for contractors very gratifying to see that the system you installed is actually operating the way that you engineered it to work. It's in the interest of contractors. It does involve a mindset change, it does involve a little training, and it does require the proper tools to get the job done. Customers that we've had that have implemented this have had huge increase in customer satisfaction. And the biggest reason you want to look at capacity testing and incorporating this into your business is simply because of better profits. When the equipment is running right, you have much more profitable service contracts. In residential and commercial, service contracts are the backbone of your business. If you're out constantly servicing your service contracts, that does not afford you the opportunity to get new business, to generate new business. You want to be able to service contract customers during off times, during the non-peak season. So these types of testing and this type of work affords you the opportunity to have a much larger service contract customer base because you don't have those callbacks, you don't have those problems that you got to service. You're going to increase your sales. Some of the contractors that have bought 435 do test in, test out. In fact, we have a contractor in Virginia that purchased those for all of his sales guys, and the sales guys go out and test the performance of every piece of equipment before they sell a new piece of equipment. And oftentimes they're the only contractor that's out that's doing that, and they're handing the homeowner a printout of what their unit's doing currently. And that says a lot about what they're doing. For me, talk about excited technicians, when you start measuring this and you start seeing it, two things happen. Number one, your technicians start to tune systems, and they start to make sure that they're doing a charge right, they're getting the airflow right, because they're actually, it's exciting to get the right results, right? When you're using a Testo 435 and you can get those results in a matter of seconds, and you see the impact on that, it does change your mindset and how you do your job. Better reputation. You have a lot more confidence in your equipment manufacturers that the equipment that the engineer is doing what it's supposed to do. I've seen time and time again. In fact, I've never seen a piece of equipment that I couldn't, if I couldn't get the airflow correct and the charge correct, that didn't output the correct capacity. You got to remember that the manufacturer engineers at ARI tested, so there's two sets of eyes on that thing. It should darn well operate the way it was engineered to operate. Improved reputation, and it's obviously got a business impact for you as a contractor and utilities for savings. So therefore, there's a little bit of training with this you're going to have to do. It's not hard. We have some kits of tools that you can do this with right on the line. You can download Enthalpy Charts for free. If you already own those tools to do that, hopefully you got a little insight on how to do the testing and how to make this work. Contractors don't know what they should know, and you really got to measure what you sell. So that is it. Thank you guys very much for attending. If you have any comments or feedback, Phil, let me see if we got any questions here that I need to answer.
There's one I'm answering now, but the rest have been answered.
Do we have any questions there?
There's
okay.
one I'm answering now, but the rest have been answered.
Okay, so everything's set there?
I think so. There was one question about using flow hoods to measure supplies and returns. I don't know if you want to address that. I addressed it pretty simply, that it's the right technique with the right equipment.
You actually have to do two measurements. You got to be really careful when you're measuring conditioned air. Number one is when you're using a capture hood to measure airflow, they're typically calibrated for standard air. And when you get into measuring conditioned air, like from an air conditioner, the humidity is actually approaching 100% as the air comes out of that duct. When I always talk about air conditioner removed humidity, you go, how the heck could it be close to 100%? Well, it's because the air is cold, and when we cool the air down, it squeezes it down, and it squeezes the water out of the air. So until that air reintroduces into the room and re-expands and re-warms up, the humidity is close to 100%. Well, a standard capture hood is calibrated typically for about 68, 75 degree air at 0% relative humidity, some at 50% relative humidity, and that humidity is going to have an impact on your airflow accuracy. So if you're measuring at the return and measuring at the supplies, let's say you had no leakage, your capture hood might indicate leakage, but it's really some inaccuracy simply because the calibration of the hood didn't take into account the change in air density. So you got to be very, very careful doing that. Capture hoods are great for air balancing. Typically if we talk about using what we want to do is we want to use a Vane anemometer to set the airflow at the equipment, a duct leakage tester like a Minneapolis duct blaster or a Retrotech DU2000 duct tester to check for leakage, and then we use a hood to proportional balance the system, okay, and to make sure we're having the airflow, the correct airflow come out of each one of the registers. But a hood is really not an ideal tool for setting the main airflow across the evaporator fan, simply because there is leakage in all duct systems that you have to take into account. So, it's not untypical to have on a typical duct system without any sealing up to 30% leakage. So what you don't want to do is have excessive air going across your evaporator coil because you used a capture hood to measure airflow at all your registers, and because then we won't have as good humidity removal. So, typically, again, small vane to do the small vane anemometer to measure airflow across the coil, capture hood to measure proportional balance, and then a duct tester to actually make sure that we eliminate the leakage. And that's the best way to do that.
There's another question just came in.
Any other questions?
Can you hear me, Jim?
Yep.
Another question just came in.
Yeah, I can hear you.
Okay. Do you measure the wet bulb in the duct or at the supply and return registers?
You want to measure the wet bulb about on the supply about 3 feet from the evaporator coil. So I typically tell somebody after the first bend, you don't want to measure it at the supply registers because you can get some heat gain. In other words, let's say you went to your furthest run in your house, right? Well, when the air came out of the register, it's going to be at one temperature. By the time it gets so far into the house, the ductwork's going to gain some heat unless it's very well insulated. So you wouldn't get a true reflection of the correct wet bulb temperatures. Typically what we'll do is because you do have to give time for the air to mix in the duct system, because when air comes off an evaporator coil, if you're too close to the coil, you might be in a cold spot or a warm spot on the coil, all right? So you want to give that time air to turn in the duct system and actually mix. So typically, 2, 3, 4 feet downstream of the evaporator coil is fine. You could even be 6 to 8 feet downstream of the coil and you'd be fine. And you want to measure the return air in the drop, or sometimes we have to measure return air at the filter rack, but ideally we measure that in the blower in the attic, because what we're concerned with when we're doing performance testing is the equipment performing correctly? Because if we have return air leakage and we're pulling in 100 degree air from a hot attic and we're taking the wet bulb measurement downstairs at the register, right? We're never going to see that hot air that's in that duct stream and be able to quantify that. There is two let me escape out of my slideshow here. Discard my annotations here. There is, too, another instrument that works really, really well for wet bulb supply and return, and it's one we just sort of put up a little while ago here. Let's see here. And my screen's still showing, right, Bill?
Yes, it is.
Okay. This is a fairly inexpensive induct cyclometer, and you can see it's got an extendable probe on it here, and you can slide that thing out, slide it into the ductwork, and get up into the return, or get up into the further closer to the blower, closer to the coil. The 605H2 is really nice because it goes in 6 inches. This is a little, if you're doing some systems that require even a little further reach inside, this is a really nice solution to that. And it uses a decent sensor in there. It's got a capacitive humidity sensor on the substrate, so it does work much, much better than like a cotton sock or wet bulb. So this is another solution. This thermometer will read wet bulb, dry bulb, dew point all together too. So it's 605H2, a little less expensive than this, more pocket size. This is a good solution though if you're doing something where you got to get a little further in the duct stream. And I believe this one will also do an averaging mode. Not 100% sure on that. I have to dig through the specs on that and see for sure. But it does get you into ductwork a little bit further. Any other questions, Bill?
Yeah, one more. 3 to 4 feet is not always possible, especially on second-story houses or ducts encased in chases.
You got to get as close as you can. There's some systems that just aren't conducive to testing, and I've seen those. I mean, I've seen in Ohio here we get a lot of slab homes, and it's really hard to get under the coil into the slab. It's impossible. So what you got to do is go to the first register, and get to the closest register you can to make your return error and make your supply error measurements, and that's about the best you're going to do at that point. So sometimes that really bites. You can see that bill just popped up there. Anything else?
That's all we got.
No, I think that's it.
Okay.
All right. Well, thanks.